This is our lesson on improper integrals. This is going to be a nice way to end our discussion on methods of integration. So on this unit, we've discovered that a definite integral was defined as a limit of a Riemann sum. We've used the fundamental theorem of calculus to evaluate these integrals. We went through many properties to solve indefinite integrals. And so now, what do we want to do if we have something that is not a proper integral? So let's start by defining a proper integral. An integral expression in the form of the integral from a to b of f of x dx is considered a proper integral if the limits and the function are bounded. So what we're saying here is, and this is important, that it's the limits and the function are bounded. They're well defined and the limit converges. There's only been a couple cases where we've seen that we couldn't take or find the integral because there was a point of discontinuity in the bounds of integration. So this lesson is going to help us decide how we take those integrals. So what we want to make sure is it's bounded on a to b. So it's completely defined. The limits of integration are finite, so there's no positive or negative infinity. And it has only a finitely many discontinuities because we have ways to deal with them. If it has an infinite number of discontinuities, then we are not going to be able to find a value for the integral. So there are a couple types, and the first type is one limit of integration is unbounded. So either a or b is infinity or negative infinity as well. And the second type is that we have bounded boundaries, we have well-defined boundaries, but somewhere in this boundary, this set of numbers, there is an infinite discontinuity, or it could be two types. So we're going to go through and see how we deal with both of these. So let's start with the most basic problem that we do with this, so where we see this. Okay, so we're going to sketch the infinite region R that lies under the curve y equals 1 over x squared above the x-axis, and then shade the area to the region of the line x equals 1. So if you look, and we're going to end at the right some value for t. We're just going to graph the positive region just to keep it simple. We can do the same thing on the other side of the y-axis, but we're just going to, sorry about that, my watch again. So it'll look the same, so there's no reason to do both sides. So 1 over x squared looks something like this, at least the positive part. It looks like this. Okay, so we want to bound this between the line x equals 1, so here's 1, and some number t over here, is we're going to bound this. And then we're looking at this region right here. Okay? Now, the idea is that eventually we're going to extend t out to infinity. So let's start with just this bounded region and solve this integral. So what we're going to do is we're going to integrate this. So this is going to equal the integral from 1 to t, excuse me, t to the negative 2 dx, I'm sorry, x to the negative 2 dx. So a of t is going to equal negative 1 over x, and we're going to evaluate that between 1 and t. So we get a of t is going to equal negative 1 over t minus a negative 1. So simplify this, we get 1 minus 1 over t. Okay, so what does the answer tell us about the value of a of t? Since we're going to get 1 minus 1 over t, that a of t is always going to be less than 1. Because this part will never be 0 because we're evaluating, or above 1. And it'll always be, we're always subtracting it, so it'll always be less than 1. Okay, so now what we're going to do is we're going to move t to the right, and we're going to look at the shaded region the whole way out to infinity. So we are going to take the limit as t approaches infinity of, and going back to where we started, the integral of 1 to t of 1 over x squared dx is going to give us this limit of 1 minus 1 over t. And as we do this, as t gets larger and larger, this value of this fraction is going to get smaller and smaller. So this is going to go to 0. So our limit is going to be 1. So even though we're solving an infinite region area, it's going to converge, this converges to an actual area which is equal to 1. Okay, so that's the idea behind this. So let's build on that idea. Okay, so next we're going to look at some different cases here of type 1. And our type 1 is, of course, that either we're only looking at one of the boundaries to be either infinity or negative infinity. So we have some couple cases of type 1. So either it converges, that means a limit exists. If it doesn't converge, if there's no limit, then it diverges. That's the first two cases. Then the third case is the improper integral requires both of the integrals to be convergent. So we're going to look at that case later. And if you look below here, this is the idea of case 3, where both limits are going to be infinity and negative infinity. So we divide that up by picking a value in that region that's well defined and splitting it up into two separate case 1s. And then we're going to just see if they both converge or one of them converges and one diverges. So both of them have to be convergent. You can't have one convergent and one not convergent. Once you find one's not convergent, it's over. You're done with the problem. It's a divergent and there's no value. Okay, so a couple hints here. Remember that when you're evaluating an improper integral, you have two problems. First, take care of the integral, then take the limit. Don't try to do them both at the same time. You really confuse yourself. And the second thing is when you're breaking down the improper integral, make sure that you're trying to set it up like a case 1, that it's only improper at one place, either the lower or the upper limit. Okay, so this one already set up to be just one limit. The upper limit is infinity, so we're going to rewrite it in this way. We're going to rewrite it as this is going to be the limit as b approaches positive infinity, and we're going to take the integral from 1 to b of 1 over x dx. Okay, so that way we're going to evaluate the integral first, and then we'll evaluate the limit. So we're going to take the limit as b approaches infinity, and this integral becomes 1 over x, antiderivative is ln of x, and we're going to evaluate that between 1 and b. So this becomes the limit as b approaches infinity of ln of b minus ln of, oops, that should be 1 now, of 1. And of course ln of 1 is 0. So what we're going to take is the limit as b approaches infinity of ln of b. And if you remember what the graph looks like, it looks like this. So it is going to diverge. It does not converge at all. This diverges. All right. So what we're going to find, and we're going to prove this later, this is connected to something that we do in Unit 10, is that we saw two different 1 over functions. One was 1 over x squared, and the other one was 1 over x. And if you notice, the limits of integration are from 1 to infinity. So this is convergent when p is greater than 1, and it's divergent when p is less than or equal to 1. And we're going to see later, we're going to have something called p-series, and we're going to have a p-series test. And what you're looking for is what is the exponent of, we'll use n instead of x. Is it n squared? Is it n cubed? Is it n? So you want to make sure that we can use that idea, and we'll prove that later on. Okay, so sometimes when you're doing this, you might have to do not only a improper integral, but it could be, like this case, it's going to be integration by parts. So we're going to take the limit, and it's our lower limit, so I'm going to use a as a approaches negative infinity of the integral from a to 0 of x e to the x dx. And then what I'm going to do is over here, I'm going to say that u is, x, and dv is e to the x. So then I can set this up as the limit as a approaches negative infinity of the integral from a to 0. Actually, I don't need it here. I can just write it down. So I can write down my uv. So I'm going to have x e to the x, and this is from a to 0, minus the integral of e to the x dx from a to 0. And so we're going to have the limit as a approaches negative infinity of x e to the x minus e to the x, and that's going to be evaluated between a and 0. Okay, so then, running out of room here, this is going to give me the limit as a approaches negative infinity of, when I substitute 0 in, I'm going to have 0 here, and I'm going to have minus e to the 0, so that's a negative 1. And then when I put a in, I'm going to have plus a e to the a minus, whoops, that should be an a, minus e to the a. And then when I take the limit, e to the a is going to get smaller and smaller because I'm going to negative infinity. And remember, the exponential graph looks like that. So as I get smaller and smaller, it's going to 0. So these two terms go away. So I get negative 1 for an answer. Okay, and then the next one, this is inverse tangent. And again, I have two limits here. So what I want to do is I'm going to set this up in this way. So I'm going to write this as the integral from negative infinity. And you can pick which number. I'm going to pick 0 because it's easy to work with, of 1 over x squared dx plus the integral from 0 to infinity of 1 over x squared plus 1 dx. And then I'm going to have to set up two limits. So I'm going to take the limit as a approaches negative infinity of this integral from a to 0 of 1 over x squared plus 1 dx. And then I'm going to add to it the limit as b approaches positive infinity of the integral from 0 to b of 1 over x squared plus 1 dx. Okay, so what I did is I took an indefinite integral at both boundaries and made it into an indefinite integral, each at separate boundaries, and now I can use my limit definition for that. Okay, so evaluating the integrals, I'm going to have, the limit. I'm going to have the limit as a approaches negative infinity of inverse tangent of x, and that's going to be evaluated from a to 0, plus the limit as b approaches infinity of inverse tangent of x, evaluated from 0 to b. So then simplifying this, I get the limit as a approaches negative infinity of inverse tangent of 0 is 0. So this is going to the upper limit here, so I'm just going to have minus inverse tangent of a, and then I'm to have plus the limit as b approaches positive infinity of inverse tangent of b, and then that'll be minus inverse tangent of 0, which is 0. Okay, so evaluating this, if you think about the way the inverse tangent is, graph as you go to negative infinity, it has an asymptote of negative pi over 2. So this is going to be, the limit is not there anymore. This is going to be negative pi over 2. And as I go to positive infinity, I have a horizontal asymptote at pi over 2. And so when I add these together, I get pi. So that's how you handle when you have both limits as being infinite. Okay, so now in this problem, example 5, we're supposed to sketch the graph, and then from 0 to 5. And why would this be improper? So the idea is here that when you see the graph, what you're going to notice is that it is not defined before 2, because you have a square root of x minus 2 in the denominator. So we have to be bigger than 2, and we can't be equal to 2 because that would be undefined. So the graph is going to look, why did that not come up? The graph is going to look like that. Okay, why would it be improper? Because if you look at our limits of integration, f of x is not defined at x equals 2. So how do we do this? We'll have to break this up. So we're going to do a one-sided limit. Okay? So we're going to write this, and this is going to have to be done integration by parts. So I'm going to let u, well actually, substitution. I'm going to let u equal x minus 2. So du is going to be dx. So I really have, let me just do the integral first. So I'm going to have the integral from, I'm going to just leave the limits off and put them on at the end. Actually, no, I can do it. This isn't a bad one. So my limits are going to change. If I put t in, I'll have t minus 2 for my lower limit. And if I put 5 in, I have 3 for the upper limit. So I really have u to the negative 1/2 du. So when I integrate that, I get 2u to the 1/2, and I'm integrating it from t minus 2 to 3. So when I simplify this, I get, I'll put it here, 2 times the square root of 3 minus 2 times the square root of t minus 2. So now we're going to have to come at it from the right-hand side because it's not defined on the other side. So we're going to take the limit as t approaches 2 from the right of 2 times the square root of 3 minus 2 times t minus 2. And when we do that, what we find is that as we approach it from the right, this is going to go to 0. So we get 2 times the square root of 3. Okay, so this is our type 2, where the improper integral is going to converge or diverge, but we have a well-defined limits of integration, but we have a situation where a point in the center, or it doesn't have to be an exact center, but someplace in that interval has a discontinuity. Okay, so we're going to be dealing with those. So you want to make sure that you look at the domain of the function. Okay, so I'm going to do one of these, and then I'll leave the other one for you guys to do. And then I will tell you what the answer is, and then we can go over it in class. All right, so number 6, example 6. So what I can see is that ln of x is not defined at 0. So what I'm going to have to do is I'm going to have to take the limit as a approaches 0 from the right. Because the function, if you look at the function here, it looks like that. So it has a vertical asymptote at 0. So if I want to get close to 0, I'm going to have to come from the right-hand side. So then I'm going to integrate ln of x dx. And I'm not going to go into a lot of details. I'm just going to let you know that I'm going to let u equal ln of x, and dv, equals dx. And so this is an integration by parts. So the limit as a approaches 0 from the right is going to be uv. Okay, so there's my u and there's my v, minus the integral of, the integral of dx, and I'm leaving my limits off right now, so this is going to be from a to 1, and this is going to be evaluated from a to 1. So that's going to be the limit as a approaches 0 from the right of x ln of x minus x, and we're evaluating this a to 1. So we get the limit as a approaches 0 from the right of, we're going to substitute, and we get 1 times 0, because ln of 1 is 0, so that's going to be 0, minus 1, and then minus, doing the lower limit, we're going to have a ln of a minus a. Let me make this a bracket. It'll be a little easier to see. So from there, this becomes the limit as a approaches 0 from the right of, and we get negative 1, hate that that splits just like that, minus a ln of a, and then we're going to have a plus a here. And when we substitute 0 in, we have our negative 1. This is going to go to 0. And this is also 0, so we get negative 1. Okay? So you guys are going to try this last example, and just to let you know, this one diverges. And this one only needs a u substitution. And that is how you evaluate improper integrals.